I've always been really fascinated by Venus because it's kind of an alternate Earth.
Some people consider Venus to be a sister planet to the Earth, or perhaps a twin. But if it is, it's really an evil twin.
I don't think it's evil, but it's a remarkably different twin.
Earth's nearest planetary neighbor is an enigma.
Venus has these incredibly thick clouds that you can't really see through.
This is what makes it shine like a beacon in the sky.
And actually, sometimes people think it's a UFO because it's so bright in the sky.
Humans have looked at Venus and been drawn to it for millennia.
To me, it's very haunting, very rich with lessons, and creates this desire to really understand that planet.
But to begin to understand Venus, we have to go there.
It's definitely mysterious, and it's of course important for science. But it became clear that Venus is a little bit easier for the Soviet Union to explore for propaganda success.
And understanding Venus could be key to our very survival.
It's about the same radius as Earth.
It was formed more or less at the same place in the solar system than Earth.
And perhaps our evolution is going to look like Venus in the future.
We can't claim to understand Earth, really, if we don't understand Venus.
For centuries, people wondered if this was what the surface of Venus looked like.
Once we realized that the other planets were, in fact, planets, the natural assumption was that, well, they're probably similar.
Venus was one of the first objects of scientific exploration for Russian science. Lomonosov, who is kind of father of Russian science, was the first astronomer who actually studied the atmosphere of Venus.
We figured out the reason why Venus is so bright and apparently featureless is because it's completely covered in clouds.
And naturally, we assume these are clouds of water, like on the Earth, in which case Venus would be a great swampy paradise. Lots of water on the surface and water in the atmosphere, totally covered by clouds. And people imagine great lizards and dinosaurs living and swimming in the lakes and oceans, the tropical forests of Venus.
Svante Arrhenius, who was a brilliant Swedish chemist, was one of the first people to actually model scientifically what the climate of Venus was like. But he also had ideas about the life on Venus and the vegetation, and he made observations that he thought confirmed this. So he actually had a kind of scientific view, but with a lot of imagination filling in the blanks, that promoted this idea of Venus as a planet with a lot of vegetation and a lot of life that was similar to Earth, but maybe also Earth sort of stuck in the past in an earlier age when Earth was sort of a swamp planet.
The only way to tell, actually, whether Venus was a sort of living world with jungles on the surface was to actually go there with spacecraft.
But before 1975, no human had ever seen an image from the surface of another planet, let alone Venus. However, a Russian mission called Venera 9 was on its way.
On 20th of October of 1975, this joint stack of spacecraft of lander and an orbiter approached Venus and separated from each other. Immediately, they started their separate missions, which were culminating at the same time. The orbiter approached Venus and started a braking maneuver with its engines to slow down its speed just enough that the gravity field of Venus would capture it and leave it into a highly stretched elliptical orbit around the planet.
This component of the Venera 9 spacecraft had become the first man-made object to enter orbit around Venus. But the mission was far from over.
And at the same time, the lander started going into the atmosphere of Venus on the side of the planet which was not visible from Earth. But thanks to the orbiter, which was so high in the sky over Venus, it would later act as a relay station for the lander to send pictures back to mission control on Earth. The lander was a ball-shaped capsule covered with a special ablative surface. And once it entered the atmosphere of Venus and started breaking, layer by layer, burning the ablative surface and at the same time slowing down tremendously from its initial entry speed.
The searing heat shield decelerated the lander from 10.7 kilometers per second to around 250 meters per second.
Then, once it slowed down enough, it was safe enough to open small opening at the top of the capsule and release two small braking parachutes. One of those two parachutes was then used to release the top part of the capsule and reveal the top of the lander, which was inside of that cocoon.
The speed dropped from 250 meters per second to 150 meters per second before a third parachute was deployed.
And once that happened, there was an antenna, a transmission antenna exposed, and that allowed it immediately start transmitting data to the orbiter, which in turn relayed back to the ground control.
The third parachute brought the velocity of the lander down to just 50 meters per second.
And then that parachute was separated, and it pulls out three-canopy main parachute system, which allows the lander really slow and gentle descent.
After all the drama of its journey so far, the lander would then spend 20 minutes calmly taking measurements of the atmosphere. But its brutal voyage was not over yet.
When the probe is around 50 kilometers over the surface, the command is sent to cut the main lines of the parachute.
Venus has always been a special object of fascination as long as we've been observing the sky, which is, probably longer than we've been people. And there's a reason for that. It's so bright. It's the brightest object other than the full moon at night.
For much of human history, we've mistaken Venus for a star, or two stars to be precise, the morning star and the evening star.
It appears as an evening star for a little while near the horizon and then disappears and then reappears as a morning star near the horizon and does this intricate little dance in the sky and then disappears again. And so it bounces from evening to morning. It's never up in the middle of the night. It's always at the dusk and dawn, which are the most evocative times. That has led it to be an object of mythology and folklore and with gods and goddesses. The association of Venus with femininity really comes out of the fact that we're still very dominated by Greek and Roman Western traditions. But in fact, that's just one tradition. And if you look around the world, for instance, the Mesoamericans, who were probably the greatest Venus observers in terms of what they figured out about how to predict the motions and everything. For those civilizations, Venus was this macho warrior dude, and it was very much a male character. So why assign a gender to a planet? Planets are at least as complex as people. So I think it maybe does do it a bit of a disservice just to say Venus is the female planet.
After the Second World War, it wasn't long before the Soviet Union stunned the world with the launch of Sputnik in 1957. A year later, the US launched its first spacecraft. The space race had begun.
The space race was driven by several major factors. First of all is the military competition of two superpowers which emerged after World War II, the United States and the Soviet Union. And the second is this ideological competition between two systems, socialism in the Soviet Union and capitalism, as at least Soviet Union saw it. And that competition included scientific pursuit. In the world of science, probably the best way to prove that superiority would be with victories in space. And the Soviet government understood this.
Space exploration has a dark side. We can't deny that we rode to the moon and to the other planets on the wings of war, that the reason we have these rockets that can launch payloads into orbit and beyond is because they were developed to destroy cities.
The emergence of rocket technology immediately gives scientists this idea that you can put scientific instruments on the rocket and fly them first to the upper atmosphere, then to space, and then into deep space all across the solar system. But within the Soviet Union, it was in the framework of testing intercontinental ballistic missiles and weapons systems. It was absolutely under the same level of secrecy. There was absolutely no public. This was absolutely top secret.
We didn't use the term spacecraft in those days. We called them payloads because everything went on top of a launch vehicle. And the main thing you put on top of the launch vehicle was the warhead, which was the payload. The idea is you were really trying to develop a launch vehicle. The payload was sort of an insignificant addition back in those days.
What happened early on in the space race is we began to say, hey, the solar system, let's explore it. And our competitors, the former Soviet Union, was doing the same thing. Now, they happened to set their sights on Venus really, really hard.
The initial motivation for the Soviet space program was propaganda success. The ideas about Venus as a tropical paradise were not at play in the process of decision to fly spacecraft to Venus. It's definitely mysterious, and it's of course important for science. But the most important factor was that it's easier to reach than Mars.
The rocket scientists in the early space race concluded that in order to get to Venus, there's a window of time in which the planets are closest. This occurs every 19 months. From the moment the race to Venus began in 1961, only 3 opportunities were missed until 1986. First off the mark was the Soviet Tyazyoli Sputnik in February 1961. It failed to leave low Earth orbit. Venera 1 became the first spacecraft to fly past Venus. But due to a communications failure, no data were received.
The early history of trying to get to Venus is full of failure. There were a lot more failures than successes.
Within weeks of the first 2 attempts to send a spacecraft to Venus, a discovery from an Earth-based radio telescope increased the intrigue about our mysterious twin. Venus was found to have a very odd rotation. The planets seemed to be rotating backwards, very slowly. A day on Venus is longer than its year.
You could say, why does Venus rotate backwards? But you can also say, why do all the other planets rotate forwards? I mean, it's a mystery. We don't really understand Venus's rotation rate. But we don't really understand the rotation rates of the planets in general.
18 months after the discovery of Venus's peculiar rotation, the next opportunity to get to Venus was approaching.
In that second half of summer of 1962, all these forces finally came together. Both sides finally had the rockets necessary to launch. They had the spacecraft, which were sophisticated enough to go to Venus. And they had this motivation, money, and all the political rationale to do this. So within this short period of time, from July to beginning of September, there were 5 missions launched, 2 Mariner probes and 3 Russian MV probes, as they were called.
Mariner 1 and 2 were identical, and they were both modified Ranger spacecraft taken off the product line and converted for a mission to Venus rather than a Ranger mission to the moon. They were hexagonal in shape with 6 boxes bolted onto a frame. There was a high-gain antenna, and there was a tower structure bolted on top of this hexagonal. We called it a bus. It wasn't at all unusual to be working 56 hours a week, you know, and if that meant everybody had to work weekends or something like that, or, you know, 16-hour days, we did it for the time that it took to get back on that schedule.
On the 22nd of July 1962, Mariner 1 launched. But the spacecraft malfunctioned and flight control had to manually destroy it. A month later, the first Soviet spacecraft, called 2MV1 number 1, succeeded in getting into orbit. But its upper stage rocket booster failed, and it never left low Earth orbit. 2 days later, Mariner 2 blasted off successfully from Cape Canaveral, followed by the final 2 Soviet spacecraft on the 1st and 12th of September. Both failed to leave Earth's orbit. 3 months later, on the 14th of December 1962, Mariner 2 arrived safely at Venus.
Mariner 2 became the first spacecraft to explore another planet in the solar system and actually return useful scientific data from the vicinity of another planet.
The measurements that Mariner 2 made suggested that the upper atmosphere of Venus was very hot, in the region of 500 degrees Celsius. Perhaps Venus wasn't quite the paradise everyone had hoped for.
There was an editorial in the New York Times when the Mariner 2 results were reported, and it was titled, "Venus Says No." And it talks about the grand romantic dreams of mankind being dashed.
Mariner 2 also made another startling discovery. There could be a hint that all was not well with Earth's twin. Unlike our planet, with its north and south magnetic poles, Venus doesn't have any significant magnetic field.
It's about the same radius as Earth. It's roughly the same rotation rate. Maybe it's 100 times slower. But that's not that different fluid dynamics-wise. These are still rapidly rotating bodies. It's got a big core, we believe. We believe it's molten. Something's funny that Venus has no dynamo.
Mariner 2 took measurements of high temperatures on Venus, and there was a dispute about those temperatures perhaps being only high in the atmosphere, or the temperatures really showing unbearably hot environment everywhere around the planet.
So of course the immediate challenge was after this, both for the Soviet Union and for the American scientists, was to launch more probes, more sophisticated ones, but design them based on already available information and continue this pursuit of what Venus is all about.
Mariner 2's distant flyby hadn't settled the score for supremacy over Venus. But the USA and the USSR were about to begin an even more intense battle for Earth's twin.
From now on, once Mariner 2 did the job, it was absolutely paramount for the Soviet Union to land on the surface of Venus first, and preferably to do imagery and science on the surface of Venus.
Over the next 11 years, there was a frenzy of missions to Venus.
Venera 9 is plunging into increasingly dense atmosphere of Venus.
About 50 kilometers up from the surface of Venus, you pass through a region that is about the surface temperature and pressure of Earth. So there's a region in the upper atmosphere of Venus that would feel pretty much like it feels in this room.
I think to any individual who reads the description of the landing sequence, thinks that it's really irrational and really bizarre way to get equipment to the surface of Venus. But after a little bit closer examination, we understand that each step of the sequence is actually logic behind it.
And in fact, it's counterintuitive, but part of the problem with a lot of designs when you're designing an entry probe for Venus is that you fall too slowly, meaning that it takes too long and you're going to heat up too much before you get to the surface. And then you keep falling, and the atmosphere gets hotter and hotter and more dense, to the point where it's 100 times as dense as the atmosphere on Earth. And that means that you're falling through, it's not quite a liquid, but it's a gas that is approaching the properties of a liquid, and that would slow your fall. And then when you get to the surface, it's almost like going through the ocean.
Venera 9 wasn't the first lander to get to the surface of Venus, but it was the first to send back pictures. It was a colossal achievement.
Venera 9 returned the first pictures from the surface of another planet. And the fact that that was done first for Venus, before the Americans did it with Viking in 1976 at Mars, is really remarkable because it's much harder to land on Venus and photograph it than it is on Mars. Not that Mars is a picnic, but just to get something to survive in those conditions and take a photograph and send the results back is really challenging. And that achievement in 1975 by the Soviet Union, well, that was a real triumph of exploration.
What we have from the Russian is just unbelievable because it was really a challenge to land there. So even if the images are not perfect, it's still wonderful.
But the ideas of Venus as a verdant, lovely environment, possibly with jungles on the surface and a water-rich environment, were immediately taken away.
It wasn't really until Venera 9 operated at the surface for some time and returned data that we were sure that we had solid data that told us, yes, this is how hot and this is what the pressure, and wow, that's really pretty intense. After Venera 9, we had a sense of what some individual places on Venus were like. If you send a probe in one place and you measure the temperature and pressure on the way down, it gives you one slice from space to the surface. But the more we learned about Venus, the more we realized that, like Earth, it's a complex, changing planet with different things going on the day side and the night side, and this latitude and that latitude, and that to really understand what's going on, you have to measure multiple places at once. If you have this probe on the night side, and this probe on the day side, and this probe at high latitude, and this probe at low latitude, and you're able to do them all at once, then you can put together more of a 3D picture of the way the atmosphere is behaving and changing over time.
In 1974, NASA approved a double mission to explore Venus, both from orbit and from multiple places around the planet. This ambitious mission was called Pioneer Venus.
The Pioneer Venus mission included an orbiter and 4 probes, 3 small probes and 1 large probe, to look at different parts of the globe of Venus and to make measurements as they descended to the surface.
The Pioneer Venus orbiter launched in May 1978, and the spacecraft carrying the probes followed it in August. The orbiter had arrived at Venus a few days earlier and inserted itself into orbit in preparation to relay data back from the atmospheric probes.
The probes were not designed to survive the landing, but fortunately, one did and continued to send back information until the heat of the surface destroyed its electronics.
The results from the Pioneer Venus mission were clear. No matter where you went on Venus, the night side, the day side, the equator, or the higher latitudes, its surface was uniformly hot and at high pressure.
So Venus is all bad. The temperature only varies by a degree or 2 over the whole globe, day to night, pole to equator, and the thick atmosphere acts like a blanket which keeps the entire surface of Venus very hot. And so there's no place, no hospitable place on the surface of Venus where we might imagine humans living.
And it's not just the temperature. The atmospheric pressure on the surface is so high that it would crush almost every military submarine ever built.
Now we see Venus is just an awful environment. I mean, the atmosphere is only CO2 with 90 bars on the surface and 500 degrees.
By the end of the 70s, we really understood how Venus looked. I mean, it was not going to be habitable.
And to me, that had sort of a lingering effect that Venus was like not as exciting as it was supposed to be, and therefore was sort of not as cool and maybe not as worthy of our attention. And I think that was really unfortunate because it was an outcome of those false expectations that we had for it.
So instead of Venus being a sort of tropical paradise, it's hell. Things have gone terribly bad. The temperature on the surface is hot enough to melt lead, and the atmosphere is full of poisonous gases and carbon dioxide.
It sets up this huge mystery. Why do you have these twin planets so nearby And one of them ends up like this, you know, this paradise for earthly life. And this other one right here ends up in such a different state. You know, what happened there? And can that happen here? And if we don't know the answer to that, how much do we really know about our planet?
In order to answer these questions, we must go back to the formation of Venus and Earth.
Earth and Venus form this set of twins that, as far as we can tell, started out more similar and then diverged. Understanding that divergence is an important scientific puzzle, but it's also just sort of compelling because Earth is our home, and here's this other planet that could have been like Earth, that should have been, and yet it's so different.
The formation of Venus and Earth was probably pretty similar. I mean, it's made of the same type of stuff.
It seems as though the original rocky stuff that fell together and made Earth probably had a lot of water bound up in it. And Venus, because it seems to have been made out of the same stuff in the same process at the same time, then likely got a similar admixture of water, just chemically bound up in that rocky material that made the original planet.
About 600 million years after the beginning of the solar system, there was a very large period of collisions when the collision rate was very high, and that's what we call the late heavy bombardment. So during that time, there are both comets and asteroids moving around, both bringing even more water to the Earth and Venus.
After all the brutal drama of the initial formation and the violence of the late heavy bombardment, things would have settled down for Earth and Venus.
Venus might have been much more hospitable. You know, very similar to the Earth. Maybe there were oceans and even life on Venus.
So why is it that Earth today is an oceanic planet and Venus is not, if they both started out similar? The one obvious difference is that Venus is significantly closer to the sun. It's about 3/4 of the distance from the sun to Earth, which means it gets about twice the amount of sunlight. When the planets were young, the sun was much less bright than it is now. So there was a time when the ocean of Venus was probably stable. What happened, we think, was that as the sun heated up, it triggered something we call the runaway greenhouse. And the way that works has to do with evaporation. So if you're evaporating the oceans of a planet, you're getting more water vapor in the atmosphere. But water vapor itself is a strong greenhouse gas, really as strong as CO2, meaning that it's a gas that absorbs infrared radiation. It lets the visible through, it absorbs infrared. So you get more water vapor, you're absorbing more infrared, you have a stronger greenhouse that heats up the surface, so you get more evaporation. And more evaporation gives you more water vapor in the atmosphere, a stronger greenhouse, hotter surface, more evaporation. So you can see it's what we call positive feedback, because the hotter the surface is, the more water vapor you're getting in the atmosphere, the more water vapor, the hotter the surface is. So each part of the cycle reinforces the other. That's a positive feedback, and that's unstable. It runs away.
So water in the oceans evaporated to make a blanket around the planet, which made the planet hotter. But worse than that, carbon dioxide was baked out of rocks.
The idea that carbon dioxide could create a powerful greenhouse effect goes all the way back to the Swedish pioneer Svante Arrhenius.
Svante Arrhenius correctly deduced that there was a lot of carbon dioxide in the atmosphere, so it was probably hot. In fact, he was also one of the first people that considered greenhouse warming on Earth, interestingly, and that partly came out of his work on thinking about what Venus was like. So this is one of the ways in which our knowledge of Earth climate and global warming is actually connected to thought about Venus, because Arrhenius put this together. He said, oh, a planet with a lot of CO2 is going to be warm.
So how did Earth escape the same fate as Venus, with a runaway greenhouse effect? The answer begins with rain.
So on Earth, the CO2 gets pulled out of the atmosphere by what we call weathering reactions, where water is raining out and makes a sort of carbonic acid, which when it runs over rocks, leaches the ions out, and it ends up in the ocean as carbonate ions and forms carbonate rocks. When you see White Cliffs of Dover or any massive deposit of carbonates, you're seeing carbon that has been pulled out of the atmosphere. Those carbonate rocks get pulled into the interior by plate tectonics, and when you have subduction of oceanic crust, down deep into the interior where they're melted, and ultimately then the CO2 is released under pressure and becomes dissolved gas, which then comes back out those volcanoes, and that completes the cycle. But that is facilitated by water in rain and in these chemical reactions. If you don't have water, you sort of break that part of the carbon cycle.
But if the process that removes carbon dioxide from the atmosphere is rain, what happened to Venus's water? The answer is due to a complex interaction of the planet's atmosphere and the stream of particles that constantly come off the sun, called the solar wind.
When the water on a planet evaporates and is in the atmosphere as water vapor, as opposed to condensed on the surface in liquid water, then it's much more vulnerable to being lost to space. And the main way that happens is the water gets broken up by ultraviolet light and what we call photodissociation, which is that these energetic photons of sunlight breaks hydrogens off from the oxygen. And then when you have a free-floating hydrogen, it's easy for that to escape into space. In fact, all planets are losing hydrogen all the time into space. And when you have a steam atmosphere and a lot of water photodissociating, then you're going to have a stream of hydrogen escaping off into space. And then after a period of time, you're left with less hydrogen and therefore less water on the planet.
The solar wind is a stream of charged particles coming out of the sun. That is what is stripping away the atmospheres of the planets. All this means that you're sort of losing water, and so Venus is becoming drier and drier. So Earth has a magnetic field which protects it to some extent from the onslaught of the solar wind, whereas Venus, we have no magnetic field to protect the planet.
A decade or so ago, people used to think that the big difference between Earth and Venus was that the Earth had a magnetic field, and then we looked at Venus and we said, oh, it's lost all its water because solar wind strips it away. We are finding it's more subtle now. Pretty much all of the planets lose their atmosphere right now at about the same rate. So everything's scrambled. We're back to the drawing board to really trying to understand how atmospheric escape works and what role, if any, the magnetic field plays in that process.
Whether or not the lack of a magnetic field had accelerated the loss of Venus's water, the planet became dry and had no chance to mop up all the CO2. But where did all this gas come from? Why was the atmosphere of Venus so much thicker than our own? To find out, scientists would need to find a way to see what was going on.
One of the fantastic things about Venus is its cloud layer. This is what makes it shine like a beacon in the sky. At the same time, it's one of the most frustrating things because it stops us seeing the surface. So what we need to do is not look with our eyes, but look with different wavelengths that can peer through these clouds and get down to the surface, such as radar wavelengths, and then we can really see what's going on.
After the success of Venera 9 and 10 in 1975, the Soviets continued to send a variety of missions to Venus. But NASA was determined to try and find out what much more of the surface of Venus actually looked like. And in the early 80s, they started to develop a mission to do that, called the Venus Orbiting Imaging Radar.
It had multiple instruments and multiple antennas, and NASA said there's no money. And so this great thing narrowed down to one instrument, and we were a spare parts mission. We used a Voyager spare antenna and a Voyager spare bus and Galileo computers, but the radar itself was a new design. It had this parabolic antenna, so the signal would ping off Venus and come back, and you have to capture it
and you synthesize an image from that, and you do it over and over and over again, and you gradually build up radar images of the surface.
The budget version of the mission, made from old spare parts, was renamed Magellan. And on the 4th of May 1989, it was delivered to low Earth orbit
12, 11,
by Space Shuttle Atlantis.
0, and liftoff.
There's the orbiter going by the launch tower.
So the design of Magellan was to get into an orbit, and if Venus is here, it would go by really close for an hour and radar image, and then it would turn back to the Earth and relay back its data for another hour, and then it would correct its wheels and get a star scan, and then turn back and then radar image again. And we did this 24/7 for a Venus day. This is 1989, 1990, 1991. We're dealing with reel-to-reel tapes, and they're running these tapes back and forth from Goldstone, and then the data from Canberra and from Madrid would actually be flown in overseas packages.
The extreme efforts that the scientists and engineers made to acquire this data was worth it. Magellan provided an unprecedented view of the Venusian surface.
They mapped nearly the entire surface of Venus. And that was a huge revelation because that was our first global look at what the geology of Venus is really like.
The Magellan data was indisputable. Venus is, or was, a world of volcanoes of all kinds.
It told us, yes, this is a world that's dominated by volcanism, has been through much of its history. It's a world that has been resurfaced by volcanism over time. There's a huge abundance and variety of volcanism on Venus. There are these huge areas of flood basalts where this running lava has come out from the interior, and a lot of Venus is covered with that. But then there are other volcanic features, these things nicknamed pancake domes, which are much smaller. They're about 10 kilometers across because they're much more sticky, less runny, more viscous magma. So it's been a volcanically active planet, massively, with all different kinds of volcanism going through many different phases. Now, it doesn't mean that it's current. It could be ancient.
All of this activity means that Venus has been belching carbon dioxide into its atmosphere for billions of years. And with no rain to absorb the CO2, the atmosphere has become thicker and thicker.
The atmosphere on Venus today is almost all CO2. And here on Earth, we're concerned about 300, 400 parts per million CO2. It's a trace gas, it's a minor gas. If we assume that Venus and Earth started out similar, which I think is likely, although we still want to gather the data to prove it, that Venus had early oceans more like Earth and had some kind of a tectonic cycle and probably a carbon cycle with carbonates and volcanoes like Earth has today, then what happened? Why is the solid part of the planet, the geology, apparently so different from Earth's? And in my view, it probably has to do with the losing of the water. That if you lose the water from the surface of the planet, then over time you're going to also dry out the crust and the interior of the planet because you are also outgassing water, you're losing water through that cycle, and on Earth you're ingassing water too, in the sense that you're pulling water into the interior all the time through that tectonic cycle. If you lose that ability to do that because you don't have any water on the surface, you're not going to right away dry out the interior of the planet. But after 1 billion, 2 billion years, you're going to ultimately end up with a dried out interior and a dried out crust. And that's going to have different material properties. And in fact, if you take an Earth model of plate tectonics and mantle convection and you dry it out, you change the properties of the rocks and say, well, what if these were dry rocks instead of hydrated rocks? These models will start behaving more like Venus. The rocks get harder, it gets harder to subduct, plate tectonics gets sort of choked off, and it's like the engine runs out of lubrication and it gets stuck and then starts going in spurts rather than running smoothly.
And this drying up of the crust could be responsible for the lack of what's known as an internal dynamo, which is what produces a magnetic field.
I think the easiest explanation for why Venus doesn't have a dynamo is probably that heat is trapped within the core. It appears right now that there's no plate tectonics on Venus. There's probably convection occurring within the mantle, but it's not very efficient at getting heat out. And so that probably traps heat within the core. If heat can't get out, then I can't cool that fluid at the surface. I can't release those dense blobs into the interior, falling and convecting. If it's not convecting, and there's none of that turbulent convection to stir up a magnetic field, I think you should then see what you do see.
Magellan orbited Venus from August 1990 until October 1994. The mission mapped 98% of the surface and greatly increased our understanding of the geological processes that have shaped the planet's history.
And by that time, it was done. You know, the computers were resetting, we were out of fuel, and then, oh, you got to update because now your timing's off because you got slightly out of orbit because of your thrusters. And it was always an engineering challenge because I was just scrambling every day just to keep it going. But it was a great spacecraft to be your first spacecraft because it was a hell of a learning experience for me.
The last communication with Magellan was on the 13th of October 1994, before the spacecraft disintegrated deep in Venus's thick atmosphere.
Well, in the aftermath of Magellan, there was a lot of desire for more Venus missions and a lot of frustration in the community of the inability to get NASA to send another mission to Venus, which is an effort that continues. But the Europeans sort of came to our rescue with Venus Express. It's called Venus Express because it was a mission that was put together very quickly. There was a spare spacecraft from another mission, and they had a couple of years to propose and fly a spacecraft, and the Venus Express mission was the one that won. And what Venus Express really is, I think of it as our first weather satellite at another planet.
And as the first Venusian weather satellite, Venus Express gave us a much greater insight into what was really going on with Venus's atmosphere.
So Venus Express made these movies of the motions of the atmosphere at different depths. And indeed, it's quite dynamic. The atmosphere of Venus does this, what we call 4-day super rotation, where the atmosphere is whipping around.
These high-altitude zonal winds can zip around the equator of Venus at 360 kilometers per hour. But above the poles, the rotational speeds drop almost to zero. The intense heat on the surface of Venus creates powerful convection currents that drive a separate, lower altitude circulation of heat from the equator to the poles.
With Venus Express, we saw these vortices near the poles, in particular the south pole of Venus, which had not been seen before. It's a little bit like water down a bath plug. So seeing that for the first time was very exciting.
Venus is entirely covered by clouds. These clouds are made up of droplets of sulfuric acid, so it's arguably the case that Venus has the worst case of acid rain in the whole solar system.
The acid rain on Venus is created by the vast amounts of sulfur released through the volcanism that has dominated the planet's evolution.
Acid rain is in an extreme state on Venus. Acid rain has been a problem on Earth, downwind of factories, and by studying it in an extreme case on another planet, it helps us understand more the interaction of acid with water clouds.
But down at the surface of Venus, things are altogether much calmer and deeply weird. Here, the wind speeds are very low. The acid rain has evaporated long before it gets this far down.
If you could go to the surface of Venus, not that we can right now, I think it would be an incredibly strange experience.
The first thing you would notice is that the quality of light would be very different from the quality of light on Earth. And that's mostly because the light is being filtered through that incredibly thick atmosphere and also through the globally extensive clouds. So it would be kind of a red, murky light.
When you look at things, you're looking through this massively convective medium where, because of the temperature you're looking at and the swirls and stuff, you see the refraction of light.
Probably would see that sort of shimmery kind of effect that you get in desert areas on Earth, just because there is a lot of infrared radiation coming up out of the surface, and that is going to be affecting the stability of the atmosphere near the surface.
You're in this really, really strange environment where any movement you feel resistance, and it becomes this viscous, fluid-like thing that you're having to move through. It wouldn't be quite like running through water, but you'd be approaching that. You'd be somewhere in between what we feel running through the air and that resistance of trying to run through something really viscous. It'd be a good workout, that's for sure.
So, in the future, will there ever be a time when Venus might have cleared its dense atmosphere and cooled enough for humans to live on its surface?
Some have proposed that Venus might once again be hospitable, and potentially after volcanic eruptions cease on the surface of Venus. I don't buy that. I think the escape rate of the Venus atmosphere over time is infinitesimally slow compared to the magnitude of the atmosphere.
The time it might take for the Venus atmosphere to be cured in that way would probably match the time that the sun would take to see out the rest of its lifetime. Swelling into a red giant and engulfing the whole planet.
So there's really no future time that I can imagine where the atmosphere would be lost enough so the greenhouse effect would be small enough so the surface temperature of Venus would be cool enough that life could exist there.
So if Venus is never destined to become the paradise we once imagined through natural processes, what about through deliberate manipulation? Can we terraform Venus?
Terraforming is an interesting concept. It's certainly a valuable thought experiment. I don't necessarily condone trying this, but that's okay because we're not going to have the ability for a long time. We have millennia to sort that out, whether we think it's a good idea. So maybe the way to do it would be to throw a lot of comets at Venus, where you would both raise up the dust from the comet impacts to cool it off, and then you'd also be sort of sprinkling it back with water. If you start to have liquid water on the surface, then that's going to restart the cycle where you're going to then be removing CO2 out of the atmosphere by weathering. It would take a while, it'd be a long-term renovation project, but there's nothing physically impossible about it. The problem with terraforming ideas is that, right now we're in a situation where we're rapidly Venera-forming Earth. That is turning it to be more Venus-like, and so we can't even imagine any of these futures unless we get to the point where we're doing a much better job of controlling our own actions on Earth.
People talk about us colonizing the solar system, escaping from the problems that we have on the planet Earth. Maybe there's an asteroid heading towards us, which one day will hit the surface of the planet and cause extinction. And I think these are things which are important, and we're studying them, and we really need to understand what the possible long-term dangers are. But there's a short-term danger, which is climate change, and it's happening today. What worries me sometimes is this idea that we can take human beings away from all of the mess that we've created here. Sociologically, it seems unlikely that we're just going to become a perfect citizen once we cross the 100-kilometer line and go into space. But also, there's nowhere in the solar system that's any better to live than the very worst that we could ever do to the planet Earth. Whatever we do here, it won't be as bad as living on Mars or on Venus or anywhere else in the solar system. So at the same time as we're looking outwards and exploring, we should never forget that this is where we come from, and there is no planet B. This place has to be looked after as well, as much as we're looking outwards and beyond.
So perhaps one day, far in the future, humankind will not only have the scientific ability to make Venus into a paradise, but the wisdom to realize that we already have a paradise of our own.